Well, hello guys, welcome back to Mr. G Physics. In this channel you will be able to improve your mark with physical sciences from grade 8 to grade 12. I'm Mr. G, and this time we're going to be doing a video where we revise the concept of free body diagram, frictional force, etc. But if you didn't subscribe yet, if you're new in the channel, don't forget to subscribe so you can get all the notifications and videos I post on regular basis. This is mostly for grade 11, however is applicable for the grade 12. The question, we're going to practice some question, and the question one say a boy is pushing a box, a 25 kilogram rock as shown in the figure. The force that is applied has a magnitude equal to 100 Newton and forms an angle of 45 degrees with the horizontal. The magnitude of the gravitational force on the rock is 245 Newton. The kinetic frictional force between the rock and the surface is 39 Newton. So as usual, the first thing we're going to do is to write the data, but in this case the data we're going to edit right on the picture, on the drawing. The mass of the rock is 25 kilograms, so let's write here mass is equal to 25 kilograms. The force he applies have a magnitude of 100 Newton. So the applied force is equal to 100 Newton. That forms an angle, and that angle is equal to 45 degrees with the horizontal. The magnitude of the frictional force, of the gravitational force, pardon, they're giving you the weight that is acting on the rock. So we are going to write it here. Weight of the rock is equal to 245 Newton, and the kinetic frictional force is equal to 39 Newton. You know now that it means the object is moving. That rock is actually moving. Draw the free body diagram of all the forces acting on the rock. So the rock is going to become a dot. And what forces are acting on that specific rock? We'll have the applied force, which forms an angle of 45 degrees to the horizontal. Maybe that force should be a little bit more inclined, like there is more or less 45 degrees. This one is the applied force. We have the kinetic frictional force pointing in the opposite direction. This one is the kinetic frictional force. We have the weight pointing all the way down towards the center of the earth. This one is the weight, and we have a normal force pointing up. Guys, this one is the free body diagram. If you do this in the exam, this should have 1, 2, 3, and 4 marks. This one is question 1.1, and it's quite important. 1.1. So now question 1.2, calculate the component of the force in the x direction and in the y direction. Yes, note that in the x direction this FA will have a component which is here. It's not part of the free body diagram, that's why I did not include it before. I'm only going to put it now. This one is FA in x, right? And this one will be equal to FA cosine of theta, which in this case is 45 degrees. Remember, this is not part of the free body diagram. Okay, so now here just calculation is quite simple. If you do calculate, and I think we can even substitute here, we get that the applied force is 100 multiplied by the cosine of 45 degrees. You will get that this component of a force FA in x will be equal to 70.71 Newton. That is the answer for the horizontal component. Okay, that's the answer for the horizontal component. Remember, once more, this should not be drawn on the axis, on the free body diagram. But this force also have the vertical component, so it will be somewhere there. There it would be, and this one will be FA in the y axis. Okay, and if we do it, we can do it on this side here. FA in the y-axis is equal to FA 10 theta. Theta is 45 degrees. So if we come here, we have that FA in the y-axis is equal to, this is the component of the in the y-axis. There we go. So that is the answer. Now calculate the normal force. Now to calculate the normal force, guys, we have to go to the y-axis. Alright, because the normal force is in the y-axis. So this is the axis we are going to be working with, the y-axis. And I want you to know that in the y-axis, the forces are at equilibrium. This object is not moving in the y-axis. So we back here, as we say, this object is not moving in the y-axis, it's moving horizontal. Therefore, the object is at equilibrium, or the forces are at equilibrium in the y-axis. Because the object is at equilibrium in the y-axis, we can say that the net force in the y-axis is equal to 0. Alright, what forces do we have in the y? We have applied force in y, we have the normal force, we have the weight, and all that is equal to 0. If we say up is positive, then we have that the applied force in y plus normal force minus weight is equal to 0. We're looking for normal, all we have to do is to rearrange for normal. And then we have everything. Everything is given to us. This is how to calculate the normal force. In previous questions, in previous videos, I told you normal force doesn't have formula. So every time you have normal force, you will have to do the same approach. Now for question 2.4. For question 2.4, they ask us to calculate, let's see, we have another question, calculate the resultant force on the x direction. So we come here and we say F net in x. Alright, what forces are acting in the s direction? So we are coming here and let's mark. We have the kinetic frictional force and we have the applied force in the x axis. So let's take right as positive and let's write it here. Right is going to be positive. Therefore, we have that is the applied force in the x axis positive minus the frictional force. Okay, if we substitute what we have here, to the right, and this is the answer. So this is the answer of this question. It's quite simple. It's a good question to practice. I hope you understand. I really hope it helps. Let's go to question 2. A large suitcase with a mass of a 32 kilogram rests on a ramp. Velocity there is 0. Is on the slope upwards and into an aeroplane's hold. The ramp is inclined 20 degrees to the ground. Draw a free body diagram of all of the forces acting on the suitcase and resolve the gravitational force into parallel and perpendicular components. In this case, I want you to solve it into components. So what we're going to do is to represent first the forces in the picture. That will help us a lot. Okay, so here, what forces are acting on that box? First of all, you have weight pointing straight down. This one is weight. You do have normal, which is perpendicular to the surface all the time, and that one will be pointing in this direction. Let's try to fix it to be a little bit better. All the way there, from there. This one here is the normal force, and then we have the friction, which is pointing horizontal to the surface in the opposite direction of the attempt of motion. This one is the static frictional force. The object is not moving there. Okay, so those are the three forces acting on this specific object, box, suitcase in this case. All we have to do for the free body diagram is to draw it on a point. So we're taking all those forces and we put it on a point. So let's do that. Let's come here and have a point here. Alright, and then let's take force by force. So let's take this one and let's take it and place it there. That is the frictional force. Let's take weight and then let's place weight there. And then the normal, we take in the normal and we bring it. Guys, this one is the free body diagram. I done it like this because people attempt to make mistakes in this specific question. There will always be 1 mark per force. However, now in this question they ask you to do it or to break into components. So let's quickly move this W to this side here. No, we're speaking about the weight because we're going to add the axis. The axis because the question asks us for the parallel and perpendicular component. So it will be convenient to know the axis here. Now the components of these forces will be, you take it here, there will be the weight in the y-axis. Remember, because theta is this angle here, this one is the 20 degree we were speaking about, then W in y-axis will be equal to W cos theta. Be careful with this one. And if you take it here to the x-axis, you have in this side here W in x. Alright, and remember W in x, let's maybe do it here. W in x is equal to W or weight multiplied by sin theta, and that is how we break it into components. Maybe make this one a little bit more clear. Cos theta, and that is the answer for 2.1. We didn't calculate the component, but we can actually calculate it and finish with this one. Okay, we don't have weight, but weight is equal to mg, so we can calculate now the component. In actual fact, let's do it real fast. And then we get that the answer is going to be 294.69 Newton. This one is the vertical component of the gravitational force. It is going to be the component in the y-axis. Now for the x-axis, let's quickly calculate it as well. Let's just take this one and move it a little bit here. There we go. So we can use, I think it's enough space for us to calculate the component in the x-axis is equal to weight. Remember, we do not have weight, but you learn that weight is equal to mass multiplied by acceleration due to gravity. That is why we substitute it here as well as we are going to do it there. So we have mass, acceleration due to gravity, sine 20 degrees, and the rest is substituting. The mass is 32, 9,8, sine 20 degrees, and the answer is 107.26 Newton. Now we have the vertical and we have the horizontal component of the gravitational force or weight. Okay, so that is all. Now let's go to the next question. Calculate the magnitude of the frictional force that keep the suitcase stationary on the ramp. Now this is a little bit tricky to understand. So let's see if we can get this one. This suitcase is not moving, therefore there is a static frictional force. Okay, that is quite simple. Now why is the static frictional force? Because the object is trying to move. Now why is that object trying to move here? There is a force that, or it's a component of a force which is trying to move that object downward, or let's say down the slope. This force here, this component of a force, is the one responsible to pulling some kind that object towards that side there of the ramp. That is the component of the force in the of the gravitational force in the x-axis. That one is responsible for making the object trying to move. Remember when we spoke about frictional force, we learned that if the frictional force is static, it will be equal to the applied force. So in other words, this frictional force is going to be equal to that force that is trying to move that object just in the opposite direction. So we can come here to this side, is enough space here, and this one is question 2.2. We can say that let's say the net force, and we're going to learn about this one is a lot later on. Net force is equal to 0 in the x axis. The object is not moving in the x-axis. Remember that one. So all we have to say is that the frictional force is equal to the weight in the x-axis, all right, and that is equal to 107.26 Newton, but the direction is to the left, okay, or up the ramp. That will be the answer for the frictional force. Guys, this is the answer. I hope you understand. Remember, we spoke about frictional force. I leave the link for those videos there. Okay, frictional force, if it's a static, is equal to the applied force. In this case, we don't have applied force, but we have the component in x to the weight. That is what we have. That is the one responsible for this one. And then question 2.3, calculate the coefficient of static friction between the suitcase and the ramp. So now this one is also quite interesting. The frictional force, this one is question 2.3. You know that the static frictional force, or the maximum static frictional force, let's say, is equal to a static coefficient of friction multiplied by normal. We don't have the normal. We don't know how much is the normal. But in the previous video, we learned how to calculate normal. We have to go all the way to the y-axis. So to calculate this normal, we go to the y-axis. We say F net in the y-axis is equal to 0. Object is also not moving in the y-axis here. What forces we have in the y-axis? Let's go back to the free body diagram. In the y-axis, we have the normal and we have the vertical component of the weight. So we know then that the normal force is equal to the weight in the y-axis, and we did calculate already that one there, which is equal to 294. You can see there 294.69. That is the normal force. It's not a formula. We have to use the free body diagram. Okay, now we have everything we can substitute. Static coefficient of friction is equal to 0.36. No unit for static coefficient of friction. This is how to solve it. However, I'm going to show you something. Alternatively, you can do quite simple. And this one is for question 2.3. Instead of doing this one, you get the 10 of 20, 10 of theta, which is 10 of 20 degree, and that one will give you the static coefficient of friction. This one is 0.36. There we go. So alternatively, you can do this one. You ask your teacher if you are allowed to do that one, and that one is quite simple to get the static coefficient of friction in an inclined plane. Guys, this is all for today. I hope it helped. This is a good two questions related to free body diagrams, calculated friction, etc. I hope it helped. If it helped, thumb up, subscribe for the channel. I'll see you next time. Next time we're going to start now with the Newton's law, Newton's first law, and we're planning to do some experiment there. Thank you for watching. I'll see you next time, Mr. G.